Hello everyone, welcome to new class. Today's class is about shift register counters. So one of the application of shift register is that they can be arranged to form several types of counters. And shift register counters are obtained from serial in, serial out shift registers. Serial in, serial out shift registers by providing feedback from the output of the last flip-flop to input of first flip-flop. And these devices are called counters because they exhibit a specified sequence of states. And the most widely used shift register counters are ring counter and twisted ring counter, also called Johnson counter. So these are the two types of shift register counters, ring counter and twisted ring counter. Let us study about the ring counter. So this is the basic or simplest shift register counter, and this is the ring counter using D flip-flop, and this is ring counter, that is 4-bit ring counter using JK flip-flop and D flip-flop. And the flip-flops are arranged as in a normal shift register. That is, the output Q, the Q output of the each stage is connected to the D input of the next stage. But the Q output of the last flip-flop is connected back to the D input of the first flip-flop, such that the array of flip-flops is arranged in a ring, and therefore the name ring counter. Similarly for JK flip-flop, here both JK inputs are given, that is here Q output of the each flip-flop is given to the J input, and Q bar input of output of the each flip-flop is given to the K input of the each flip-flop, and the last output is feedback to the JK inputs. So there are 4 flip-flops, and this is the sequence table, and this is the state diagram. So initially the first flip-flop is preset to 1, that is the Q1 output is 1. So the initial state is 1 0 0 0, that is Q1 1, Q2 0, Q3 0, Q4 0, and after each clock pulse the contents of the register are shifted to the right by 1 bit. So after each clock pulse, the content of each flip-flops are shifted to the right by 1 bit. For example, this is 1. So after the first clock pulse, this Q4 output is applied to the J input, that is J becomes 0 and K becomes 1. 0 1 means this Q1 now becomes 0, and the previous Q1 output is shifted to J2 input, that is J2 now becomes 1, then 0 here. like that each flip-flop is shifted to the right. So these data is shifted to the right by each clock pulse. The number of distinct states in the ring counter, that is the mode of the ring counter, is equal to the number of flip-flops used in the counter. So for an n-bit ring counter, it can count only n bits. So an n-bit ring counter can only count n bits, whereas in the case of n-bit ripple counter, it can count 2 raised to n bits. So for ripple counter, it can count up to 2 raised to n bits. So the ring counter is uneconomical compared to a ripple counter, but has the advantage of requiring no decoder, since we can read the count by simply noting which flip-flop is set. And since it is entirely a synchronous operation and requires no external gates, it has the further advantage of being very fast. So this is about the ring counter. Next is twisted ring counter or Johnson counter. And this counter is obtained from a serial in, serial out shift register by providing a feedback from the inverted output of the last flip-flop to the D input of the first flip-flop. And the Q output of each stage is connected to the D input of the next stage, but Q bar output of the last stage is connected to the D input of the first stage. Therefore the name twisted ring counter. And this feedback arrangement provides a unique sequence of states. And this is the logic diagrams for 4-bit twisted ring counter using D flip-flop, and this is using JK flip-flop. So here in using JK flip-flop, Q bar output is connected to Q bar output of the last flip-flop is connected to the J input of the first flip-flop, and Q output of the last flip-flop is connected to the K input of the first flip-flop. And this is the sequence table, and this is the state diagram for the 4-bit twisted ring counter. So initially all the flip-flops are reset, that is 0 0 0 0. All the output states are 0 0 0 0, and after each clock pulse the level of Q1 is shifted to Q2, then the level of Q2 is shifted to Q3, Q3 is shifted to Q4, and Q4 bar. So here Q4 bar is connected to the first flip-flop, so Q4 bar is shifted to the Q1. So by looking the sequence table, after the first clock pulse, the Q1 is first 0, but Q4 bar is connected to J. So after the first clock pulse, this is 1, then this is 0. So when 1 0 in JK input, Q will be 1. So we get this 1 here, and previous 0 is shifted to J input. So here 0, 1. That means Q2 is 0. Then again after the second clock pulse, this one is shifted to J. So again in the previous case Q1 was 1 and that 1 is shifted to Q2. And again this Q1 becomes 1 and this repeats after. So after the fourth clock pulse, Q1, Q2, Q3 and Q4 becomes 1. Then Q4 bar will be 0 at that time and that 0 is shifted to J. So after the fifth clock pulse, this Q1 will be 0. Then all others 1, 1, 1. Then after 6th 0, 0, 1, 1. After 7th clock pulse 0, 0, 0, 1. After 8th clock pulse we get the initial condition, that is 0, 0, 0, 0. So there are 8 states in this 4-bit twisted ring counter. So an N flip-flop Johnson counter can have 2n unique states and can count up to 2n pulses. So we can say that it is a mod 2n counter. So ring counter is mod n counter and a twisted ring counter is mod 2n counter. But this twisted ring counter is less economical than the ripple counter, but more economical than the normal ring counter. So this is about the shift register counters, that is ring counter and twisted ring counter or Johnson counter. Thank you for watching the class. If you like the classes, please like, share and subscribe my channel.